Alright, so for this we will be looking at our rates of change and our derivatives homework solutions. For the first part here, you are told that you have the area of a square is increasing as the length of the side increases from s equals 1 inch to 5 inches. So here what this wants us to do is write an expression for the rate of change in this given situation. So our rate of change here is going to be the rate of change of the area versus the side length of the side. So here we're going to write this as the rate of change of A over the rate of change of S, and that's going to be equal to A at 5 minus A at 1 over 5 minus 1. Now, if we keep in mind that our area is equal to our side squared, then we can actually number crunch this on out. So that's going to be 25 minus 1 over 4. So that's going to give us 24 over 4, or 6. Okay, so question 2 is the surface area A of a cube decreases the length of the side S of the cube decreases from 9 to 2 centimeters. So for this one, keep in mind that this is talking about your surface area. So surface area formula is 6 times your side squared. And so for this, if we're talking about, again, that rate of change of the area with respect to your side, then keep in mind here's your formula. So it's going to be 6 times 9 squared minus 6 times 2 squared, and that's all over 9 minus 2. And so number crunching this, that's 484 minus 24 all over 7, and so that rate of change is 66. Okay, looking at question 3, we have the area of a find the area of the equilateral triangle decreases as the length of the side S decreases. So for this, we're going to look at, again, the area of that equilateral triangle. So we're going to look at dA over ds is going to be equal to, now the area formula for an equilateral triangle is going to be root 3 over 4 times your side squared. So there's our formula. And so now we're going to be substituting in, and for the first part, we are subbing in here our 12. So you're going to have root 3 over 4 times 144 minus root 3 over 4 times 16, and that's going to all be over 12 minus 4. So that's going to be equal to, so in the numerator, those are going to cancel, giving me 36, and this is going to cancel here, leaving 4, and 36 minus 4, we have 32 root 3 all over 8, and so then that's also going to give us 4 root 3. And for this one, notice that that area, it should be a decreasing because it is getting smaller, so that area here is going to be a negative rate. Okay, so for question 4, we have the volume of a sphere, and so we need our volume formula there. So over here to the side, we know our volume is going to be 4/3 pi r cubed, and don't worry about trying to remember these formulas. It will be given to you. So the volume of a sphere increases as the radius r increases. So here we've got the volume increases with respect to the radius, And so we're increasing from r equals 3 to r equals 8. So here again we know 8 minus 3. And in the numerator, when you sub in and number crunch all this out, do leave pi in your answer. You should have 2048 over 3 pi minus 108 pi over 3. And again, just number crunching, by all means use a calculator. And so this is going to give us 388 pi over 3. All right, so now let's look at question 5. So after a drug is injected in the bloodstream, the effectiveness decreases slowly over time. C at T is the drug concentration. Write an algebraic expression for the period between 0 to 4 hours after the drug has been administered. So again, we're going to be talking about the change in C over the change in T, another way to write it. And so for that one, it's going to be, we're going to start C at 4 minus C at 0, and that's going to be over 4 minus 0. All right, for questions 6 through 9, we have the graph of a function talking about a golf ball being hit. And so notice the first part in 6, it wants us to draw a line tangent to this graph at 4. So we're going to come in and draw us a line the best that we can there, right? And now number 7, it says to estimate the instantaneous rate of change at time t equals 4 and to show our work that leads to the result. So it looks like if we're going to be time at 4, then a good estimate, we could use our other time frame maybe to be at 3.9. You could do 3.99, whichever. So again, using your calculator, this would be a calculator work. We're going to say that h at 4 minus h at 3.9 over 4 minus 3.9. And when you number crunch that, then you're going to get approximately, and I hope you get a negative. We see that that tangent line is negative. So negative 18.8. And again, go back and find your units. That is going to be your feet per second. Okay, so in number 8, what is the mathematical name of this instantaneous rate of change? That mathematical name is a derivative. And why is that rate negative? Well, the rate here is going to be negative because our function, or we can think about as the golf ball, is decreasing. And or you could think of the golf ball is returning to the ground. Either way you want to. Think about it. Both are correct. The golf ball is returning to the ground. So both ways are good ways to think about this. Okay, in our next question, it says Amy was walking to the bus stop when she saw the bus approaching. She started to run towards the bus but couldn't catch up. The bus left before she could get there, and so Amy had to walk the rest of the way to school. So what it wants us to do is try to sketch what's going on here. So let's think about this for a moment. So she was walking to the bus stop when she saw the bus approaching. So she was just walking. I don't think she was probably walking all that fast. So maybe she was walking up till, let's say, 1, 2, 3. So I don't think she was having a huge amount of rate of change. But as soon as she saw the bus, well, then she took off running. Okay, so I would say her rate of change did speed up. But once she saw that the bus was going, then she returned back to her walking pace, which should be about close to the original slope we drew. So hopefully you have something similar to this. Okay, in problems 11 through 14, you have these scenarios, and notice that it wants you to draw a velocity versus time graph, which represents the motion described in the grids below, and draw a horizontal axis. Label the axis appropriately with its units. So here, notice it does give you a graph. It's 250 plus 150 sine of t, where t is your time. And it tells you to store this function. You don't have to do that. That's some of the older stuff. So here, don't worry about that. Now, we do need to do a good sketch, though. And we have 250 plus 150 sine of t. So at time 0, then we're up here at 250. So if we just go ahead and use what we know about a sine curve, we know it's going to do something like this. Now, as we know that, then notice what's happening with our tangent curves. If we start sketching those, then notice that in this region here, notice that rate of change there, and that's going to be positive, and that's because you are increasing. Important to know that. And then down here, notice that this line here, which by the way has a slope of 0, this is constant. And then over here on this other side, if we draw in our line there, that is going to be decreasing. So you have a negative slope. All right, let's look at our next part. In 12, notice that we need to estimate the average rate of change of the raccoon population for time t equals 1. The change in R at t from 1 year to t is R at t minus 1. So complete the table of values for R at t at each. So looking at this, we need to go through and complete our table. So you are going in and substituting in values. Do make sure you're set in radians. All right, so the first one here, R at 0.99 minus R at 1, that's going to give us 81.610. If we number crunch the other, we're going to get 80.478. And then the other, we're going to have 74.605. So in part A, it wants to know, well, which is the best approximation? And so the best approximation looks like it's going to be from t equals 1 to t equals 1.01. Okay, so in part B, it says, what does this rate mean regarding the raccoon population? So to answer that, the raccoon population is increasing at year t equals 1. Okay, so now let's look at 13. It says the instantaneous rate of change, R at t at 1, is the limit R at t approaches as t approaches 1. So use the numerical derivative feature to determine the instantaneous rate of change. So that numerical feature that this is talking about on the calculator, if you will go to menu, and then you're going to select calculus, and then you're going to have just your first derivative, and then it may also ask you for a value, and so that value that you would put in is 1. And then you should be able to type in your function, which again they gave you that was your R at t. Remember that function was R at t is 250 plus 150 sine t. And so you're going to type that in. Again, make sure you're in radians. And so when you do that, hopefully you'll get an answer of approximately 81.045. And that's raccoons. Oh my, I'm going to run out of room. Raccoons per year. Okay, so now in 14, it's asking you to approximate the instantaneous rate of the population changing from 4. So explain why this one might be negative. So if we're going to estimate that, then again, to set this up, we need R at, and let's get super close to, we don't need that many zeros. Let's just do that. Minus R at 4, but you're welcome to put in those more zeros if you want to, over 4.001 minus 4. Okay, so that's going to give us about negative 98.364. And that is raccoons per year. And so to interpret this, that means that the population is decreasing. All right. Okay, so number 15, the number of E. coli cells. P at T at time T in hours in a petri dish is plotted to the right. Now we need to draw a secant line over the time interval from 1 to 3. So at 1, and you can, let's see, 1 is going to be right here. And so I know that's going to be 1, the ordered pair 1, 2000. And then up here at 3, then that's going to be 3, 8000. Okay, and so now we need to draw a secant line. So let's try to connect those the best we can. Okay, so there we have our secant line. And so that's the first part. And now it wants us to calculate the average rate of change at P at T. So to find that average rate of change, which again is going to be our slope here, take your ordered pairs. You have 8,000 minus 2,000, because again, you're really just calculating that slope over 3 minus 1. So that's going to give you 3,000. And so what that means is you have 3,000 bacteria per hour. All right, so now let's look at part B, estimate the instantaneous rate of change at the point 1, 2000, and we need to use a tangent line passing through that point. And so they want us to show a tangent line there, and so I think that tangent line is really being shown. That's what's in red there. So to estimate that here, then goodness, if we go through and find another point on that line, so I've got this point, and if I look through, I've got another point right out here that I could use, because this is a tangent line. And so whatever the slope is on that line is going to be the slope at that point. So I have 4, it looks like 6,000. Okay, now let's use this point here and this point here to calculate a good estimate for your rate of change. So I'm going to have 6,000 minus 2,000. Over 4 minus 1. So that's going to give me 4,000 over 3. And so that's going to be about 1,333, pulling a bunch more 3s. And that's going to be bacteria per hour. Now it says here, explain what the slope represents in the context of the problem. And so it's important that we say in the problem itself. So we're talking about E. coli, not slopes, so we have to be careful here. So notice this was an estimate at 1. So what we're going to say is at 1 hour, the E. coli, so stay in context of the problem, E. coli cells are growing at a rate of, and this is where we're going to use our estimation, 133.333 cells per hour. And finally, number 16, each position graph shown below represents the particle motion of a function of time. So we need to match this. So looking at part A, so we have a position graph, and so we're looking at the speeding up. So as this is speeding up, then we're kind of thinking about a slope. What is going on with that slope? Notice it just says we are strictly speeding up. That's it. So I think A should go over here. Okay, so now let's look at B. B says that we are speeding up, then slowing down. So speeding up, then slowing down. So here, I think this one we're speeding up and then we're starting to slow back down. So I think that's B. Now C is just slowing down. So I think this one, you're right, you're just slowing down. So that's going to be C. And so that means this must be D, which is slowing down, but then notice it changes to speed up.